Quaternionic zeros as a resolution for mathematical singularities. Mathematics is the language we use to describe reality. Operations involving zero can produce undefined or indeterminate results. Let's investigate zero not as an empty void, but a perfectly balanced structure. This animation shows the concept. A calculation on the number line hits a singularity at zero. This is the concept of quaternionic zero, defined as a sum of one real component and three imaginary components in perfect balance. So a conceptual quaternion zero, or a 4D zero, can be understood as the perfect equilibrium between two concepts. The perfect equilibrium is achieved by having a dimension of measurement for all four concepts, equally. We represent all of these as a sphere with spin, thus compressing four dimensions of measurement into one singular representation, also known as a quaternion. When working with quaternions, a key benefit is that zero is not a conceptual nothing, but rather a quaternionic balance. This reconceptualization resolves multiple mathematical singularities, including division by zero, indeterminacy, and limit paradoxes. The problem with dividing two concepts by zero is that at least two dimensions are required to represent them. The arithmetic of real numbers and more general numerical structures called fields leaves division by zero undefined, or leading to a singularity. By using quaternions to represent latent space between two concepts that we represent as real numbers, we can accurately represent the latent space between these dimensions with only adding two additional dimensions. The spin after the singularity can be represented simply by calculating the time, or distance from singularity, that has passed and the location in 3D complex space as an additional two variables. When we project these quaternionic rotations down into two-dimensional graphs, understanding the conceptual zero becomes more important than just a simple balance between two concepts, but between four different concepts equally. Imagine we are looking at a system of four competing concepts, each pulling from the center into its own quadrant. We have the blue concept, W, pulling everything to the right, and its opposite, the green concept, Y, pulling to the left. At the same time, the red concept, X, pulls upwards, while the purple concept, Z, pulls downwards. These four forces are in a constant tug of war. The white result vector in the middle represents the compression of all four quadrants. It's the net result, showing which direction the system is currently leaning. The equilibrium, or the quaternionic zero, is that special moment when all forces are in perfect balance. You can see this when the blue and green forces are equal, and the red and purple forces are equal. At that point, the white vector vanishes, and the system finds its stable, balanced center. Notice how the four concepts compress into the center. For quaternion components, real A and imaginary I, J, K compress toward the origin. In linear, they glide straight inward as their magnitudes ease to zero. In spiral, they rotate while shrinking, folding their paths into the center. Both modes finish at a strict zero, A equals B equals C equals D equals zero, demonstrating perfect quaternionic balance. The Kagome pattern is vertex transitive, meaning every vertex has the same configuration of surrounding shapes. This uniformity contributes to its visual harmony and structural balance. The internal angles of equilateral triangles, 60 degrees, and regular hexagons, 120 degrees, complement each other. Around each vertex in the Kagome pattern, two triangles and two hexagons alternate, summing to 360 degrees, which is essential for a seamless tessellation. As a 3D rotation, representing the orientation of a 3D cube. The duality. Two interpretations of one thing. The duality is that the same four numbers, W, X, Y, Z, from the control panel are being used in two completely different mathematical ways at the same time. Interpretation 1. The 3D cube as a rotation. In 3D graphics, A quaternion is a single, indivisible object that represents a rotation in 3D space. All four numbers work together to define a single orientation. The W component, the real part, and the X, Y, Z components, the imaginary parts, are mathematically linked. When you check normalize, we force the quaternion to represent a pure rotation. The 3D cube's orientation is the direct mathematical result of applying this single rotation. Interpretation 2. The 2D hexagon as magnitudes. In the 2D hexagon, we are ignoring the rules of quaternion rotation. Instead, we are treating the four numbers as simple, independent magnitudes or forces. W and Y are opposing forces on one axis, tilted 45 degrees. X and Z are opposing forces on the other axis. The white node you see is the final equilibrium point, or the vector sum, of this four-way tug-of-war. What you're seeing is a visual representation of a lattice morph, driven by a single control parameter. The field of particles starts in a perfect Kagome lattice. You can see the distinct pattern of hexagons and triangles. As the morph value changes, the entire structure fluidly transforms. Every node moves along a predefined path, until it seamlessly clicks into a completely new, stable formation, a perfect triangular lattice. This oscillation shows a continuous, breathing transformation between two complex geometric states, all governed by one simple value. Let's go back to an equilibrium chart, with each variable plotted over time. As the main chart seeks equilibrium, or a balance state, the combination vector will oscillate around. We can divide a hexagon into 12 Brillouin zones. These four variables, W, X, Y, Z, create a state moving in this latent space, or Brillouin zone. But this 2D path is just a compression. It's a shadow of the true motion. That same balanced state is simultaneously perceived as a pure rotation in 3D space. What you're seeing isn't just a random pattern. We have 12 distinct zones, each visualizing the 2D equilibrium state of a single central quaternion. All 12 zones are being animated by the exact same four variables: W, X, Y, and Z. When we arrange these 12 projections in 3D space, they perfectly tile to form a rhombic dodecahedron. This shape is the first Brillouin zone of a face-centered cubic lattice. You can think of it as needing 12 dimensions to fully describe the state of this single four-variable quaternion. But this 12-sided shape is incomplete. It's the skin, but it lacks the central 13th component, the remaining cube of compressed energy. We can think of this missing core as the vacuum energy of the system. This cube will be the focus of another video. For now, let's focus on the 12 perspectives of the quaternion value. This central quaternion value will be one of the three foundational pillars in the symbolic high-dimensional SHDCCP universal atom packet, which is a hyperbolic language standard for general AI to AI communications. Looking back at the 12 two-dimensional perspectives, let's focus on the resultant vectors of all 12 hexagons. This is displayed with the gray oscillating nodes. Let's turn persistent trails on and change the colors to see the oscillations easier. As the node trails oscillate and move, they allow different Brillouin zones to be selected and latent space data to be triangulated from the central quaternion in 3D space. This simple feature of projection allows hyperbolic data to be compressed into a central 4D structure. In 2D space, this can be represented as a circle in a square, and tiled infinitely. However, 3D projection gets more complex. This will be where representing the quaternion as a single compressed cube in 3D space helps easily and accurately represent and recreate hyperbolic data, assuming one has the codecs to translate or decrypt the data. This four-concept compression, or cubic compression, is what makes quaternions a powerful tool in the toolkit of any algorithm developer. Finding the balance state and expressing accurately to a high precision any deviation from this equilibrium is the foundation of establishing a universal standard communication protocol. Subscribe and follow along for further updates to the SHDCCP Universal Neural Symbolic AI language, and how quaternionic zeros as equilibrium states play an important role in 0-1 constant time algorithms.